So another TMUA paper by someone who likes the channel, Zetta. So thank you to him for writing this. It's supposed to be a little bit harder than the normal TMUA paper. Let's see how it goes. Apologies for being away from YouTube for so long as well. In case this is the first video you're watching in a while, I thought I would take a little break while I got on with actual work that I'm paid to do instead of this, and I'd done a lot of it before, so yeah, I just need a little bit of a break. But anyway, now we're back into it. Let's integrate this. Of course, it integrates to a over 2x squared plus 2x, integration with respect to x, of course. Put in the a, put in the 1, and you end up with this. You can double everything. You can cancel some things down, like these 2's, for instance. And then, of course, you can just start solving this. Now, how do we solve this? Well, what we can do is we can just solve by inspection. We can just try putting in 2, which clearly doesn't work because you wouldn't get a root 2 over here. If you put in root 2 cubed is actually 2 root 2, and then plus 3 root 2 makes 5 root 2, and so therefore root 2 will be the answer. We'll do a lot of using the answers given to find the correct answer in this video. So yeah, that's the first example of that. Now here we have a circle that must look like this if it has center A0 and radius R. Now we can put in this point here, and actually that's basically all that we need to do. Because if we square root both sides, of course, squaring a negative is the same as squaring a positive. If we square both sides, we get this. And now if r is plus r, then we just end up with r minus a equals 2. And if r was minus r, we wouldn't end up with that. We'd end up with like r plus a. But it doesn't really matter, right? We have that r minus a equals 2. So therefore, I think it's 2. Now, so there, the answer of C. Now you can check this, right? You can put in the other points if you want to, and you can work out a properly by substituting in this r squared into this here to get an equation in A, and you can solve for A, and then from A you can solve for R. But in any case, you'll eventually find the answer is 2. This is TMUA, right? So we should maybe be trying to be as fast as possible with our solutions. Of course, you can cancel the logs here to make this equal to this, and now all we're going to have to do is solve this, but then check whether or not the answers make negatives inputs into our logs, because we're not allowed to have that, obviously. So of course, this is very quick to solve. You notice when you look at the answers over here that this is going to factorize to 13 and 7. Which gives you this, and now when you put in positive 7, you get minus something over here, so that's not an answer. When you put in negative 13, you're going to get positive on both of them, so 13 or negative 13 is the only answer. Next here, now this is almost a geometric series, except for this minus 6, so we'll just cut it here and say it's minus 6 plus an infinite geometric series, starting at x and having a common ratio also of x. So what we'll say is that this p of x is equal to minus 6 plus the sum to infinity of that geometric series. And of course, if p of x is 0, we can just solve this very quickly and we'll end up with 6/7 as our answer. Number 5, so this game here has someone scoring 1/4 of the team's points and someone scoring 2/7. Now, what that means, of course, if the number of points scored is a whole number, which I'm going to assume it is because this is a basketball game, the total number of points scored must be a multiple of both 4 and 7, such that you can take 1/4 of it and 1/7 of it, or 2/7 of it, and get a whole number. So okay, well the first multiple of 4 and 7 is 28, so let's just try that. 1/4 of that would be Alexa's points, 2/7 would be Brittany's, and then Chelsea always scores 15. But this adds up to more than 28, so that can't be it. The next multiple of 4 and 7 is 56, so just double all those numbers except for Chelsea, who always stays at 15, of course. This leaves behind 11, which seems like a reasonable number for 7 other team members to score if none of them score more than 2. And of course it's one of the answers, so therefore I think it is the answer. Split this into partial fractions. I didn't do partial fractions properly. This one comes up so often that I just know it's this minus this, and of course you can very quickly check this n minus 1 over n on top, which makes 1. So okay, that's fine. And if we're summing from 1 to 6,000, just put in that bit by bit. So put in 1, you get 1 over 1 minus 1 over 2. And then when you put in 2, you get 1 over 2 minus 1 over 3. And when you put in 3, 1 over 3 minus 1 over 4, and so on. But of course, this half cancels with this one, and this third with this one, and this quarter with this one, all the way until the end. And the only things you'll have at the end are 1 over 1 and this minus 1 over 6001, because those two things have nothing to cancel with. And so the answer will be A. Question 7 looks absolutely horrendous, but it's the second question where we're just going to use trial and error to find out which answer it actually is. So we have an equilateral triangle, sides 1. Now the angle here is 60 or pi over 3, so the area is just a half times 1 times 1 times sine pi over 3, which is half times root 3 over 2, which is root 3 over 4. Now A4 is just a square length 1, so therefore it's area 1. And an over an plus 1, when n is 3, must just be this over this, which is root 3 over 4. Now, that means that apparently this is a constant for each, sorry, not I didn't mean that. It doesn't mean that it's a constant for every single one. So A5 over A4 might be, or sorry, A5 over A6 might be different to this. However, if you put in n is 3 to any of these answers, it should get you this one here. Now, all I have to do then is just put in 3 for all of them and see which ones do. Now, it's possible that more than one will, in which case I'd actually have to work out A4 over A5 and then check whichever 2 or 3 satisfied the one I'm checking now. But it turns out when you check this that only one of them does it anyway. So yeah, just go through this very slowly, know your tan values, and you'll see that this one doesn't work because the 4 is on the top when it should be on the bottom. When you do B, you get this here. Again, you can just calculate this, put the tan values in, tan 45 is 1, and you end up with the right thing once you rationalize that. So B ends up being correct. Of course, the 3's cancel 3, and you get root 3 over 4. So B is correct here, and then of course you just need to test all the others, because they could also be correct, but then be incorrect for a later an over an plus 1. But of course tan 90 you can't do, so this one goes away straight away. D doesn't quite work because tan 150 is negative, so we'll cross that one out as well. E you have to check as well, doesn't quite work, and neither does F, and so we're all good to go, and B is the only one that works. 8 I'm not sure about, because the only way I figured out to do 8 is use year 2 expansion with powers of halves, which I don't think I'm really allowed to do. Essentially all I said here was of course that this one cancels with this one. This one is tiny, and so I'm going to ignore it, and so the only term I'm left with is this one here, which just ends up being exactly B. I don't think I'm really allowed to do that, so answers in the comments for how I'm supposed to do that using stuff that's found in the TMUA spec. Let me know, because I don't think I'm allowed to do that. But anyway, question 9. So okay, well this circle, I don't think I ended up using this. I think I just wrote it down because it seemed like a sensible thing to write down, but I don't think I ended up using it. This circle has this equation, and the curve of course has that equation. All I'm going to do here is I'm going to put this value into here, which actually gives me a quartic in 4, but it's not really a quartic, it's just a fake quadratic. So I'm still going to do the discriminant check on this fake quadratic, because this circle only touches the curve, it doesn't intersect it, it just touches it. So b squared minus 4ac should still be 0, even if it's a quartic, because a quartic is just a fake quadratic. This quartic, sorry, is just a fake quadratic. So I can just do b squared minus 4 times a times this c here. And yeah, we'll end up cancelling a bunch of stuff, which is really nice, and then it just kind of very easily turns into E, which is cool. Question 10. So I've actually written an entire worksheet of questions for a class. I did it a few years ago, of questions just like this. You just break the 3 into a 1 plus 2, and then you can factorize the inside here to be this thing squared, because it's 1 squared, minus 2 of the cross terms, and then plus root 2 times root 2. Then of course you need to be careful here, because the root of something squared is not the something, it's the modulus of the something. Like if you have a is minus 6 here, minus 6 squared is 36, and then you root 36 for 6. So that's why the mod thing happens, because this root only finds the positive value, so therefore that's where the mod is from. So of course this actually isn't 1 minus root 2, it's the mod of 1 minus root 2. 1 minus root 2 is a negative number, which is why this matters, and so the mod makes it positive by making it root 2 minus 1. And so this is the answer here. Yeah, this is roughly how I felt when doing this question, because I have spent a lot of time writing questions like that. I might put that worksheet I made a few years ago into the description below if I remember to, and if I don't, someone can comment and I'll add it in. Anyway, this question here, so just cross multiply that thing out, and then a little bit of rearranging. Like this term seems sensible to move over, because then you end up with something that factorizes to a plus d squared. And actually it works out really nicely, because over here you get 2 lots of a plus d, and this is actually another quadratic just in terms of a plus d. So you could maybe replace it with a letter in your head, and this factorizes obviously to this, so therefore this one factorizes to a plus d minus 1 all squared, and a plus d needs to be equal to 1 to make that work, just like y needs to be equal to 1 to make this work. So I think this is Bayes' theorem. I can't really remember, but I didn't use that. I just said that I just wrote the entire sample space of rolling 3 dice where 2 of them give you a 3. So here's the sample space when the first 2 are 3s, and then you have all of these where the second 2 are 3s. And notice I've skipped this one because I've already written down the 3 3 3 case, right? And then here's it when the first and third are 3s. Again, skipping this one because I've already written it down. And of this entire sample space, only one of them has the third one also being a 3 out of 16 total cases. So it's 1 over 16 for our final answer. This question is really cool because it's very easy to get it wrong. If you just call the sides of the square 1, then this thing here is obviously a half, and this one is 1. And this length here, likewise all of these lengths, is going to be just root half squared plus 1 squared, which is root 5 over 4, which is root 5 over 2. So that's cool. So that's each of these lengths. Now it's very tempting to just say that the area of the grey square now is just root 5 over 2 times root 5 over 2 to make 5 over 4, and then the area of the face is 1, right? And so the answer is 5 over 4 over 1, which squares to, 25 over 16, because they're asking for r squared. However, that's not quite right, because these angles here are not 90 degrees. This is not a square, it's a rhombus. So first we need to work out this angle in order to then be able to work out the area of the grey square. So this length here is root 3, CE, because it's just 1 squared plus 1 squared plus 1 squared square rooted. And now we can use cosine rule on this CEI triangle to work out the angle theta that's in between here. Now I'm just going to do this quite quickly because it's pretty boring, but eventually you end up with this, and you can now use sine squared plus cos squared equals 1 to work out sine squared or sine, which is this, and that cancels down to, did I write it down anyway? This is supposed to be 4 root 6 over 10. I think I put this in first by accident. But the area of this grey square is 2 triangles, each of a half AB sine theta. So that's just this working here with this being sine theta of this angle, and then the 2 sides being what we had earlier. This all cancels to this, which is this. And then r, of course, is the area of the grey square, which is root 6 over 2, over each face, which is just 1. And then, of course, we can square that. Finally, this comes in. It's bad timing. Anyway, then we can square that for 6 over 4, which is 3 over 2, which will be our final answer over there. So yeah, good question. You just have to be very careful. So if we tan inverse this, the first solution is x squared plus y squared equals pi over 4. So this here is pi over 4. So the r squared is pi over 4, which means the r is root pi over 2. So the area, therefore, of this circle is pi times this squared, or just pi times that, which is pi squared over 4. Now, the next solution is, well, tan repeats every pi, right, or every 180. So just add pi to it, and you get 5 pi over 4. And then, of course, root it to get that this distance is root 5 pi over 2. But, of course, the area of this whole circle is just pi times this squared, or pi times this, which is 5 pi squared over 4, which means that the area of this annulus is this whole circle, which is that value, take away that value, which, of course, is just pi squared. And now, of course, we can just do a over c. It's this over this, which is, of course, just 4, and we'll have our answer. Number 15. Apparently, I'm not supposed to use trig functions, so I'm just going to completely cheat instead. So I actually don't know how to do this with trig functions, so that's not helpful. If we call this y and just let x be 0, arctan of 0 is 0, and sine of 2 times 0 is still 0. So whatever answer we have, it must have answer 0 when we put in 0. So if I put in 0 to this, I get 1 over 1, which isn't 0. So that goes away. So does this, so does that, and so does that. These are the only two that make 0 when you put in a 0. This one, arguably, well, it makes 0 of 0, which I would have maybe allowed if I didn't later work out, but it was definitely one of these two. Next value to put in, maybe just put in 1 over root 3, because arctan of 1 over root 3 is pi over 6. 2 pi over 6 is pi over 3, and sine of pi over 3, I believe, is root 3 over 2. So we're now aiming to look at these two and find the one that when you put in 1 over root 3 gets you root 3 over 2. So let's find that. This ends up being, this is C I'm testing here. That ends up being this, which roots to this. This makes a root 2. Sorry, this makes a 2, and then the root 3's cancel, so it's just 1 over 2, which is not root 3 over 2. So then we just quickly test D, and it turns out that D works, which is nice. So yeah, good. D is the answer. 16 then. So I don't know whether this is the only way of doing this, but it immediately came to mind for me to write this one as A over A, because that's just nice, right? A over C plus A over B plus A over A. Just makes that nice little triplet there. And likewise down here with B over B. And then if you just combine all these fractions together, you get this, which allows you to cancel the A, B, C from both divisions there. And then if you factorize back out the A from the top sentence and B from the bottom sentence, this thing and this thing ends up being identical, so you cancel them, and you end up with A over B equals 17. Now that means that A equals 17b, and because these are only positive integers, we can start with B equals 1, and A has to be 17. Which means, of course, A plus 2B is 19, take it away from 50, and you get 3C has to be less than or equal to 31. And again, if C is a positive integer, that just gives you this list of C's. to make that. And that's 10 things. That's 10 ways of doing it. But then, of course, we can just set b as 2, which gives us a as 34. 34 plus 2 lots of 2 is 38. Take it away from 15, get 12. Ugh, have I got this maths wrong? I have, but I don't think it's going to matter. This should be a 12, right? But it ends up having the same 4 solutions, so therefore it should be 4 plus 10 is 14, and when b is 3, you end up being over 50, so you can't have any. So A will be our final answer. Number 17 then, so let's just call the radius of the small circles 1. And then if we look at this distance here from there to there, we know that's r plus 1. And then if we go across, because this distance is also r, and this distance is also 1, this is r minus 1. And here, because this distance is r, and this distance is 1, 2, 3, this is r minus 3. So I think I can set up this Pythagorean equation, just expand everything out, cancel a bunch of things, factorize, and you end up with r equals 9 is the only valid answer, and of course 9 over 1. So question number 18 then, let S be the set of all points between 0, 1 and 2 in 3D space, picking a value between 0, 1 and 2. How many equilateral triangles can we make out of these points that all exist in here? Well, I started by thinking about the two-dimensional case, and also just with the numbers 0 and 1 rather than 0, 1 and 2. And obviously there are no equilateral triangles here that you can make. So now let's make it into three dimensions by having those 8 coordinates as our choices, between, again, just the points 0 and 1 to choose from first. Now I can find some equilateral triangles here, like for example this one that goes across root 2 because it's 1 squared plus 1 squared is rooted, and then again across root 2 to this black one, or sorry, to this red one, is again root 2 to there, and then root 2 up to the other red one. But likewise, you could have gone to this black one instead, and then this to this black one along the top edge here is still fine, like that would have still worked. So there are actually 2 you can make from this corner, either going there to those 2 red ones, or going to this black one and this red one, sorry, and this same red one over here. If you count up all of those little root 2 triangles, you'll end up with 8 of them. There's a few different counting strategies you could use, including sort of thinking of this one as having, okay, so you've got a base of this edge going along this corner, and then you can tilt it over to be part of this one instead, so it goes across here up to there and down. But then do the same thing with kind of this base edge, it goes either to there or to there, and then do the same thing with the top edge going this way, and there are 2 of every single one, so that's 8 in total. Now, when you get to the bigger case, where there are 3 numbers to choose from, 0, 1 or 2, this is essentially just a bigger cube, and you can think of it as just being 8 of the smaller cubes put together. And so if each smaller cube, these little 2 by 2 cubes, have 8 of the root 2 triangles in them, then this bigger cube has 8 times 8, which is 64 of those small triangles. And now all we need to do is think of the bigger triangles that we can fit in here. So for example, if we put the biggest triangle we can in, which goes all the way across here, side length root 8 or 2 root 2, it's just a triangle twice as big as the ones we were just drawing. Logically, there still must be 8 of those in the same way that there were 8 of the ones that we just saw, because we've just done a twice as big triangle and a twice as big cube. So there's still 8 of those to do, so that's going to be 64 plus 8 to get there. And then we also have these really hard to spot triangles, which are actually length root 6, because it goes across or back 2, up 1. 1 squared plus 2 squared plus 1 squared is 6. This is kind of a root 6 triangle. And how many of those are there? Well, if we start on the black corner here, we can do 2 of these from this corner. We can either go up and across to this red and then up across to this green, or go to the green instead over here and then to the red over there. And then you can just pick your 4 sort of black X's here to pick first. Each of them has 2 of these triangles that can be built from it. They're all going to be unique, and so therefore I think there are 8 of those as well in that particular type of triangle. So the answer is 64 plus 8. Which is not 80. Yes, it is. It is 80, right? Yeah, 16, which is 80, which is good. Question 19 then is an interesting one. So we're solving this log equation. So clearly the 2 can go up here and we can cancel the logs. Now we need to be careful here in the same way we were previously. That, of course, when we solve this equation, we don't want to have any negative inputs in these logs. Or maybe we do, because we're looking to have exactly one real solution. So if we solve this quadratic and have cases for k where there are 2 solutions, maybe we can make one of them deliberately negative, and only one of them deliberately negative, such that, or negative enough, such that some of these inputs don't exist, and that will give us one solution as well. So we get this quadratic, and of course we can set b squared minus 4ac equal to 0, to solve the boring case where we do just have one x solution, and we get either k as 0 or k as 8 for one x solution. Now k as 0 clearly doesn't work because you end up with log of 0 here, which isn't a thing, so we can't have that. But k equals 8 does give us one legitimate solution for x, one real solution for x, and we could verify that by putting k as 8 in. We get x is minus, so this will give us minus 4x, so it factorizes to minus 2 minus 2, so x equals 2 as a solution. So that's fine, that inputs into both of these quite nicely, and we end up with nice stuff. So k equals 8 is definitely a way to get one real solution. The problem is, as I said, there may be more, because I could get two solutions for anything where k is bigger than 8 and anything where k is less than 0. I get 0 solutions for between 0 and 8, so we can discount any of those values. But less than 0, that will give me two solutions, but if one of them was sufficiently negative to knock out maybe this log, and the other one wasn't, then we'd only have one solution in total at the end, right? So that's what we're going to aim for. So there's a bunch of ways of thinking about this, but drawing the graph is quite a nice start at least. If we draw the graph, it looks a bit like this, because it has, for some value of k, because it has an x value over here, sorry, a y-intercept over here of 4, this is this quadratic here, and this turning point is, well, if you complete the square, it's half this number, it's going to be 2 minus a half k. So this turning point is minus 2 minus a half k, I guess. And now let's just think about what this graph does. If its turning point is over on the right-hand side of the graph, that means because it must go through this point, and because x squared is always positive, it must have these two positive solutions. And if the curve has two positive roots or solutions here, then that means, because both of these are unaffected by being positive, they're fine in logs, that means that we won't get that one missing or that one incorrect value that we want. So if the turning point is over here, then this just isn't going to happen. It's not going to work. So let's just set this turning point here to be greater than 0, and you end up getting that k is bigger than 4 to get there. So k equals 4 is when you, of course, end up with the symmetrical quadratic in the middle when you get x squared plus 4. So you end up with the middle one. The moment k is bigger than 4, its turning point kind of slides down and down this direction like this, with the curve becoming bigger and bigger down here, down this way. Now, when x is 8, exactly equal to 8, you end up with this curve we discussed before, where we have one solution. So that's the exceptional case. When k is 8, it's fine. But when k is bigger than 4, anything bigger than 4, we either have 0 solutions, of course, when it's just kind of like a small curve up here, or we have two solutions when it comes too big down here, and they're both positive, and so they won't be knocked out. And k is positive as well in everything we're discussing here, so it doesn't mess up this one over here either. So that's all good to go. So what about k negative? And k negative could cause problems because, of course, it makes this log, the input, negative. But if the x solutions were negative, that would be fine again. Now, if the x solutions were negative, that would mess up this one, except if one of them was not sufficiently negative enough to mess it up. Like if one of the solutions was negative 1, then this one wouldn't be messed up. Like if the solutions were negative 1 and negative 10, and k was like negative 5, that would all be fine, right? We'd have one solution of that negative 1, because this one would become positive, and the two negatives here both times would make positive as well. So what actually happens here, so at most we have 501 solutions, I'll just say, because we'll have the 500 between 500 and minus 500 and minus 1, and we'll have that one solution at k is 8. So at most the answer is 500. Is there any reason to knock out two more? Or is there any justification we can give for why all of those 500 work? Well, thinking about moving this k value along, and you can do this in Desmos if you want, or GeoGebra or whatever, it works out quite nicely if you type it in and put k in as a slider. This turning point kind of moves up in a parabola of its own. It's a nice little proof that it does that, that you can do if you'd like to. And the turning point kind of moves in an upside down parabola like this. And so when k becomes more and more negative, you end up moving further and further down, making the pathway bigger and bigger, but like this. But what you notice about all of these things here, and the red one, by the way, represents when k is 0. Of course, that represents the other time we had one solution. It doesn't count because this doesn't work, but all of the other bigger k's, the k's further than 0, or the negative k's, because you have to go through this point every single time, you have to go through at least one value here between between 0 and negative 2, which is exactly what I was saying I wanted, because one root between negative 2 and 0 here makes this positive. The other root, which is a bigger negative number, makes this not work. And then because k is negative, and because both roots are negative here, this other root is never going to be positive because it has to go through here still. And we are always going to end up with exactly one solution to those ones there. So 501 is totally the correct answer. And just a really nice question with some good logic in there being used. Now, number 20, I've linked this paper in the description below, but number 20, I should have maybe said at the start, had a misprint, so I've just retyped it down here as what it should be. So, okay, how do we do this? Well, what we'll do is we'll just set f of x equal to g of x, and of course times by 1 plus x squared, both sides. Now we can expand this out, and then we can times it by f of x everywhere. And now what we can do is we can write out 2012x. Now f of x has a 2009 in it, so I'm going to cancel that from both sides immediately, and then write out the rest of f of x without the 2009 on the first line. Then this is 2x f of x, and then this is x squared f of x. Now what happens if you add these together? Obviously the 2010 and the 2009 don't, sorry, the 2010 doesn't have anything to work with, but the 2009s you notice just cancel immediately, and then you notice the 2008s all do, which is brilliant, and then the 2007s all do, and then you just kind of hope that that happens the entire time. You verify that the x squareds also do it with each other, which is fantastic, and so then you assume the x cubed stuff. There's of course some nice logic you can use that shows that all definitely goes away, but of course what I'm going to argue here is that the only thing left is x to the 2010, and these two bits here, which make plus 2010x. We can divide everything by x, of course. X equals 0 I think is a solution, but it's not interesting according to the question, so we end up with this, and then our solution is just immediately this, which is B, which I forgot to underline, apologies, but the answer is B. Thank you so much for watching, and thank you to Zetta for writing that paper. I thought it was really fun, really fun paper, which is well worth people doing, I think.